Okay, hello. So the point of this video is to, as quickly and efficiently as possible, cover section 15.4. Um, just enough so that I'm just going to talk enough so that if you finish this video, you can finish this worksheet, which you hopefully got. Then if you finish the worksheet, that should be enough for you to finish the homework. And then if you finish the homework, that should be enough for you to bring me questions. And then next Thursday, we have the quiz on this stuff. So on Thursday, the 26th, we've got the quiz on 15.3 and 15.4. So let's just get right into it. I'm going to try to do this as quickly as possible so you have a lot of time to work together and get through the worksheet and maybe even start the homework. So 15.4 is about surface area. Please excuse the handwriting issues here. I'm writing on a 15-year-old drawing tablet that it's not working as well as it used to. So whatever, but this is my handwriting today. So this is surface area. You already know how to make a surface. To make a surface, you just write an equation in terms of two variables. So anything f of xy, you've got a function floating here, f of xy, then you can turn it into a surface by just declaring that z equals f of xy. Then you get this two-dimensional object. So like you could make a cone, or you could make a sphere, or you can make a plane. Anything where you just have like x's and y's, you get a surface out of it. We already know how to find the volume. To find the volume under a surface, you just do the integral of z dA, like how high the surface is times the base area. This is like base times height gives you volume. Or some of the more complicated problems had you do the integral of top minus bottom dA. Again, the top and the bottom would be surfaces. It'd be like the top surface and the bottom surface. They'd both be in terms of x and y. Then you'd get some integral. Depending on how these integrals went, you either did rectangular or cylindrical coordinates. So those are the integrals we did before. Today, the new thing is we need to figure out, well, what is the formula going to be for the surface area, as opposed to the volume? Okay, so to do that, we have to recall a bunch of things. First thing is we have to remember how to find the area of a parallelogram. Parallelogram. The area of a parallelogram is now that you have vectors is not too hard. If you have two vectors just going off in some direction, you can use those two vectors to make a parallelogram. Just like connect them, and you get this two pairs of parallel sides. And then the area of this parallelogram is like however long the first one was times however long the second one was times sine of theta, so that you'll get the base times the height. But this old thing told us that the area of this parallelogram is actually just the magnitude of u cross v. So if you ever need to find the area of a parallelogram, which we will here in a second, then all you have to do is find the two vectors. Well, find two of the vectors that go along the edges of the parallelogram, cross them, that gives you another vector, then take the magnitude, and that gives you the area. So this is the area of a parallelogram. Now, what parallelograms are we actually going to find the area of? Well, we're going to take our theoretical complicated surface that we're trying to find the area of and break it up into little tiny bits. So you've got some surface, I don't know, it's some like wavy object surface up here. But if you zoomed in really close, and cut up the surface into little tiny slices, so we'll slice it this way. And then we'll also slice it the other way. So imagine you've got some, I don't know where you're getting your surface from, but it's like a mountain range, or it's like terrain, or it's like an object that has some like undulations in it somehow. If you sliced it up into little tiny boxes, the boxes might not actually be boxes because they might be like at an angle depending on where you are. So the boxes you'll actually get when you zoom in, they're going to be these parallelograms. So this is our plan, is that the surface area is going to be, well, add up all the little tiny surfaces. So add up all the little tiny surface areas. And the little tiny surface areas are the little tiny pieces of surface area are parallelograms. How do we find the area of a parallelogram? Well, we're going to have to find two vectors that make the parallelogram, and then cross them and find the magnitude. So that's going to be the plan to get the formula to work. We're going to find two vectors that make up the little tiny parallelograms on the surface, cross them, find the magnitude, and then integrate it to add up all the little parallelograms. Okay, so what vectors actually make up like the surface of a surface? So you've got some surface. Here's one I made out of our worksheet. If you want to zoom in really close and see what parallelogram you get, well, the vectors that make that parallelogram are going to be the ones that are just like going along the surface. And the way to get vectors that go along a surface is to use tangent vectors. So to make our u and v so that we can make our surface area formula, I need two tangent vectors. Luckily, we made some a long time ago. You can get two tangent vectors to any surface kind of for free. So two tangent vectors to z equals f of xy. There's lots of tangent vectors, but these are the two free ones that you get with partial derivatives. Fx, like the x partial derivative of the function, that tells you how much the surface goes up if you go in the x direction by 1. So if you go in the x direction by 1, and you don't go in the y direction, then you'll go up by the x partial derivative. This is one of the tangent vectors. And then the other tangent vector is, that's easy. There's lots of tangent vectors, but these are the two easy ones. Are don't go in the x direction, instead go in the y direction, and see how high up you go in the y direction. That's 0, 1, fy. If we cross these two vectors, then we'll get, and take the magnitude, then we'll get the area of our parallelogram. And that's what we'll integrate. So here's u, here's v. Let's do u cross v. I feel like we've crossed these two vectors before. But yeah, what you end up getting when you cross these two vectors is minus fx in one slot, minus fy in the second slot, and 1 in the third slot. So it's pretty hard to read, but this says u cross v. If you have your two tangent vectors and you cross them, then you'll get this weird vector here. So all we need to get our surface area formula is to find the magnitude of this cross product. And that's not too bad. So this gives us our surface area formula. It's the double integral. So we're going to add up all these little parallelogram areas. And the area of the parallelogram is the magnitude of this vector. Fx, fy, 1. I guess these minuses are in here, but they don't really matter. So we're going to find the magnitude. Wow, worst magnitude bars, worst absolute value bars ever, but there they are. So we're going to find the magnitude of this vector. To do that, well, you do the square root of each one squared. So this is going to be our final surface area formula. Square root, we get fx squared plus fy squared plus 1 squared. That's just 1. Call this dA. So this is our formula. I'm not going to make you ever like derive the formula. That's not really what the focus of this particular calculus class is, but I always want to show you where the formulas come from. And what you should imagine happens when you do the surface area formula is you look at a little bit of area in the xy plane, that's this like dA, and then you look up above it, and up above dA in the xy plane is this like parallelogram. It's like maybe off at an angle because the surface is all wobbly. The parallelogram has an area, and the area of the parallelogram is this like weird, it's not even weird, it's just like the size of this cross product. And that's where this formula comes from. I just don't want you to think of the formulas as being like random stuff. So that's the formula. You should put it in a box, bring it on a note card, or memorize it. one of those. It's a pretty good formula. Let's use it some. So I'm going to need some space to do this. First thing we're going to use it for is, I'm going to find the surface area of a sphere. Now, you maybe already know the surface area of a... Wait, did I screw up my... Hang on a second. Uh-oh. There we go. I'm not an expert in open broadcasting software. Okay, here we go. Perfect. Not perfect. Give me just a minute. Okay. Okay, we did it. Okay. So we're going to find the surface area of a sphere. Maybe you already know the geometry formula for the surface area of a sphere. Whatever, we're going to do it anyway. So say example. Find the surface area of, let's do just a hemisphere so that it's easier to make the formula. So we'll find the surface area of a hemisphere of radius r. R is going to be bad. I'll probably use radius a in most of the problems because r is going to be needed when we do the integrals. So we'll make the radius of this hemisphere be a. Okay, so what you should do is you should say, oh, great, well, I know how spheres work. I'll just center the sphere at the origin because I get to pick where it goes. In the homework problems and in the worksheet problems, you're going to get this option of, well, the question just has a geometric shape and you can put it wherever you want. You should put the most important point at the origin. So for a sphere, it's the center. For a cone, it's like the point of the cone. It probably has a better name, but I can't remember. Any object, if you get to pick where 0 is, put the specialist, most special point at the origin. So we're going to do x squared plus y squared plus z squared equals a squared. This is the whole sphere. If we just want a hemisphere, then we can just do the top part, which is we'll solve for z. And you can tell that I did the top part because normally the square root would have plus or minus, but I just picked plus. So this will be my surface. This is my f of xy. Okay, so to find the surface area, we're going to have to go, okay, that's fine. I need to deal with the bounds. This is how all the double integrals work. Deal with the bounds. That'll decide what to do with dA, whether I'm doing rectangular coordinates or cylindrical coordinates, and then deal with the function on the inside. So let's deal with the bounds first. This particular issue is going to show up for the cone problems too. What are the bounds for a sphere? Well, what you need to think about is if you looked down on the sphere from above and looked at what it looked like what the widest part of it was on the xy plane. If you look down on a sphere, the biggest part of it on the xy plane is a circle. And that's what you should draw for your bounds, because the bounds happen in the xy plane. And the bounds for a sphere of radius a are going to be this circle of radius a. So the bounds are, we're not doing the whole circle, we're just doing the top half, but the bounds are going to be the, did I say we're not doing the whole circle? We're not doing the whole sphere, we're just doing the top half. But as far as looking down on it from above, it still looks like a whole circle. We're going to go all the way around theta from 0 to 2 pi. And then r is going to go from 0 to a. Notice that because it was a circle, I decided to do cylindrical coordinates. You shouldn't try to do this in rectangular, it would be a mess. So yeah, that's great. That's our bounds. Because we picked our bounds, we now know that dA is going to be r dr d theta. And now all we have to do is deal with the function on the inside. So the function on the inside involves the x partial derivative and the y partial derivative of our surface. Erasing the question to finish the question. So let's find the x and y partial derivatives. Fx is, well, the square root is a 1/2 power. So it's going to be half times the inside to the minus half. That puts the square root in the denominator. So 1/2 times that quantity to the minus 1/2. But since I had to say that quantity, that's why I have to use the chain rule. So I'll multiply by the derivative of the inside, which is minus 2x. 2's cancel, and I get minus x over this square root. I don't really want to write this whole square root again, so I'm just going to write z, because it says right down here that that's what it is. Then I'll do fy. Fy is going to be the same thing. It's got, I mean, the same thing at first, just the chain rule will be different. What we get from the chain rule this time is minus 2y. So when the 2's cancel, we're going to get minus y over z. So the thing we actually need to integrate is square root of fx squared plus fy squared plus 1. Let's just get what that looks like. That's going to be x squared over z squared plus y squared over z squared plus 1. And by z, like z is not actually what's going to show up in the integral. I'm just writing z because I don't want to write the square root repeatedly. But if I take all these objects together, this tells me exactly how to set up my integral. I've got the bounds, I've got the differential at the end, the dA, and I've got what the function's going to look like. So put it all together and finish the integral, and hopefully it matches up with the geometry formula. Otherwise, we're doomed. Yeah. Okay, so that integrand, the function on the inside, if I put all that stuff on a common denominator, the common denominator would have been z squared. And then if I remember what z was a square root of a thing. So z squared is actually really easy. Z squared is a squared minus x squared minus y squared. Seems great. Bunch of stuff cancels. The top is just square root of a squared. The bottom is this thing, square root a squared minus x squared minus y squared. Still working on the integrand. Remember that we're going to end up doing our integral in cylindrical coordinates. So I don't actually want these x's and y's, but luckily I remember that x squared plus y squared is r squared. So finally, the integrand that I'm actually going to use is a over square root a squared minus r squared. So let's finally write the integral. This is the surface area of the top half of a sphere of radius a. It's an integral from 0 to 2 pi, and an integral from 0 to a of this integrand, a over root a squared minus r squared, r d theta. At this point, I am very happy that I got to have that r. Without that r, I'm stuck in like arcsine and all kinds of unfortunate stuff. But because of this r, I can do a u substitution. So this is just excellent. U is a squared minus r squared. Du is minus 2 rdr. So rdr has a minus a half du. So this integral has a minus a half floating on it. So I'm going to leave the r bounds for now. This is r equals 0 and r equals a. And then rdr, I've handled that, that's du. And the denominator is square root of u. So oops, this d theta is still here. So we're doing this u integral. This is the integral of u to the minus a half. That's going to be 2u to the 1/2. So copy all this down. Integral 0 to 2 pi. Integral 0 to a. I'm going to have this a still, and 2u to the 1/2. Here's 2a u to the 1/2. Wait, I did the integral. Why did I write the integral again? Just did the integral. then we plug in a and plug in 0. If I plug in a for r, it all goes away. So all that's going to happen is when I plug in 0. So this is actually pretty cool. Really sorry about the handwriting thing. If I'm going to do more of these, I need to get better technology. But plug in a, you get 0. Plug in 0, you get 2a times the square root of a squared. That's 2a squared. So the minus a half and the minus 2 cancel, and you just get the integral from 0 to 2 pi of a squared d theta. This is, careful about the integral of a squared. It's not a cubed over 3, it's a squared theta. So the final answer is 2 pi a squared, which is right, because the surface area of a sphere is 4 pi a squared, and this is just half the sphere. So we did it. We got the surface area of a hemisphere. Okay, I've used a lot of time. We're just going to fly forward here. Feel free to pause me, obviously, because I won't be offended if you pause me. It's weird, I wouldn't be offended in person if you paused me either, so you should definitely feel okay about pausing a video. But here I go erasing everything and flying forward to the next thing. So the last two, I'm just gonna, well, this other problem I'm just gonna set up to show you how it works to set it up. The question is to find the surface area of this plane, z equals xy, inside of the cylinder r is less than 1. Let me make sure. Yeah, that's good. Okay, so wait, did I say that z equals xy is a plane? Because it's definitely not a plane. X and y are multiplied together. If it was x plus y, it would be a plane. So z equals xy is some crazy thing. We're trying to stay inside of r equals 1. And we want to find the surface area. No problem. Inside r is less than 1 are the bounds. So that's a circle of radius 1, which, I mean, okay. By now, the circle of radius 1, we're definitely going to do it in cylindrical coordinates. Circle of radius 1 goes all the way around, so theta goes from 0 to 2 pi, and r goes from 0 to 1. Then the surface area integrand is the square root of fx squared. So what's fx? Fx is y squared plus fy squared plus 1. So this is our integral. You should notice that the integral has serious problems. The serious problem for this integral is it's got x's and y's, and the integral is r and theta. So, oh, look, x squared plus y squared is here again. X squared plus y squared is r squared. So now we have an integral, and hopefully this integral is possible. Yeah, this r makes it all possible. So again, if you wanted to finish this integral, you could let u equal r squared plus 1. And then the du would handle the r. So you should feel like no matter what the surface is, as long as it's solved for z, you can find the surface area of it. Once it's solved for z, you have this formula that just says, yeah, take that function, find its partial derivatives. You don't even have to think about like a parallelogram and partial and like tangent vectors and stuff, because that's already done for you. It's all in the formula. So you get the surface in terms of z, you plug it into the surface area formula, that gives you the function on the inside. Then the hard part is going to be, oops, this wasn't the function on the inside. The hard part is going to be dealing with the bounds, because it always is. So the bounds are remember they're in the xy plane, and so if you can envision your object, then it's going to be like, if you look down on it from above, what's like the farthest out it gets, and those will be your bounds. The note I wanted to make about the volume versus surface area formulas is that volume problems and surface area problems, because of this, are like equally hard, because the problem for both of them is just the bounds. So if you can get the bounds working out, then it'll be fine. The only other thing that's a little weird here is getting different shapes of cones. So the 4th page of this worksheet is about cones, and that's because the homework problem has a cone too. The homework problem wants you to find the surface area of a cone, which is pretty good. It's a good problem. I, on the worksheet, asked you to find the volume of a cone, which is like almost the same difficulty of problem. But just something good to know is that if you want to build cones in like with an equation, the easiest way to make a cone is z equals r. This is the same thing as z equals square root x squared plus y squared. This makes a cone that every time you go out from the origin by some amount, like say you go out by 2, that means you go up by 2. That's what z equals r tells you. It says like however far out you go, that's how far up you go. That's exactly how you would make a cone. But there's lots of different kinds of cones, and the main way that you get different kinds of cones is by having them have different slopes. So z equals like 2r is also a cone. It's just a cone that's twice as steep. And z equals like a 10th r is also a cone. It's like a really, really flat cone. It's like barely a cone at all. It's almost a flat plane. So however the cone is given to you, the main thing you're going to have to find is you're going to have to find this ratio. It's kind of like a slope. It's like how far up does it go compared to how far out it goes. So if you have a really tall, but like a really tall cone with like a very little radius, then this number will be a big number. If you have a, yeah, basically it's like the height divided by the radius. Yeah. Because if the cone was like z equals mr and m is some number, and you said like, wait, what is this m? What is it? Well, you would just solve for m, and you'd say, oh look, it's the height divided by the radius. So however your cone is given to you, you should be able to get an equation for it like this. Z equals a number times r. Just find the number first, and then deal with the cone after that. Okay, hopefully that's enough. So try to get through this worksheet. There's like a 5-page worksheet. After you get through the worksheet, you've got problems. There's only like 3 homework problems from this section, so try to become an expert at those. And then this section and the section before it are on the quiz next Thursday. So thanks for playing along with this. Hopefully it worked out. Send me questions. I probably won't get to your emails until next Monday, but yeah. Cool. Okay, have a good rest of the day. Bye. Wow, I can't make it stop. Okay, bye.